So let me begin. Let me remind you the definition of Ramsey number of graphs. Excuse me. So for graph G, the Ramsey number of G is defined as a minimum integer n, natural number, such that for every 2 edge coloring of Kn, there exists a monochromatic copy of G. So by 2 edge coloring, I'm coloring the edge set of the complete graph in 2 colors. So I'm assuming that you're fairly familiar, or at least have seen this definition before. Okay, so Ramsey number was first introduced in 1930 by Ramsey, where he was interested in a problem of formal logic and then used this definition as a tool to prove some result in formal logic. Then in 1935, Erdős and Szekérys, they found a geometric application of Ramsey's result. Actually, I have to state Ramsey's result. So Ramsey. 30. Ramsey number of complete graph is finite for all t greater than equal to 1. And he actually gave an explicit upper bound, which is which has been improved by Erdős and Szekérys. So
he did for hypergraphs.
Also for hypergraphs, yes. So his theorem is not just for graphs, but also for hypergraphs. And I wanted to so his result actually implies that the Ramsey number of all graphs are finite, because you can always take a complete graph on whatever number of vertices you're interested in. So in 1935, Erdős and Szekérys found the geometric application of it and gave the following explicit upper bound on the Ramsey number. So what they proved is, in fact, a recursive relation that gives this bound. So since then, it became really popular and people found more applications, a lot of variants, and now it's one of the most active areas of research in combinatorics, the whole field of Ramsey theory. Okay, what did I want to mention next? So this bound is essentially 2 to the 2 plus little o of 1 t. And the best known lower bound was established by Erdős in 1947. He proved that R of kt is essentially 2 to the 1/2, at least 2 to the 1/2 times t. This shows that Ramsey number of complete graphs is exponential in terms of its number of vertices. And really, this is a historical result marking the beginning of the probable listing method. Maybe not the very first, but one of the earliest.
So that it won't look
1947.
Now here it looks as if the lower bound is equal to the upper bound.
Okay.
Yeah.
Thank you. Thank you.
Since this is being videotaped.
Okay. Thank you. So in around 1950, people knew that the Ramsey number of the complete graph is exponential, and it's between 2 to the 1/2 times t, 2 to the 2 times t. So a lot of people were interested in trying to improve these constants in the exponent, 1/2 and 2 since then, and everybody failed. So there has been some small improvements. So this little o of 1 term had been improved, and these are considered significant improvements, but still nobody was successful in improving these constants. So it will be a major breakthrough if somebody succeeds in doing it. Okay, so that's what I wanted to say. But about complete graphs, what about for more general graphs? So we know that the Ramsey number of complete graphs is exponential in terms of the number of vertices. Is that always the correct behavior? And it's not that difficult to see that it's not always exponential. So one example is if you consider, so graph G, a matching. Okay, so if you have n vertices, n over 2 edges, then it's really easy to see that the random number of this graph is linear in n. So giving a linear upper bound is easy. So it doesn't have to always be exponential. However, I would say the following theorem of Sudakov from 2009 is one of the best results towards establishing a general upper bound on random numbers of graphs. So he proved the conjecture of Erdős and Graham. And show the following theorem. So if G has m edges, there exists an absolute constant C such that for all m, if G has m edges, then the random number of G is at most 2 to the C square root m. Okay. So in some sense, this shows that complete graphs have the largest possible random number. Well, maybe the exponent, maybe there exists graph with the same number of edges as a complete graph with larger exponent, but no other graph can have random number going faster than exponential. Because if you have n vertex graphs, always satisfy m at most n choose 2. The number of edges at most n choose 2, meaning if you have an n vertex graph, the Ramsey number is at most exponential in the number of vertices. Okay.
But doesn't this follow also from the fact that the Ramsey number of k?
That's true. You're right, yeah. Oh, you're right. That's an easy way to see it, I guess. Okay, so this is a general upper bound. However, unfortunately, as you can see from this example, it's not the whole story. So if you fix a number of edges, there's still a lot of variety of possibilities you can have on the random number of the graph. So although the best possible general upper bound you can give is this 2 to the square root of number of edges, some of the graphs might in fact have linear random number. So can you actually use the structure of the graph itself to go beyond this bound? That is one question that I would like to talk about today. Before doing that, let me show you actually the proof of this lower bound. It's a really simple proof. Proof of Erdős 1947. So I will take n to be 2 to the t minus 2 over 2. And what I would do is color. So I have to give an explicit, not an explicit, I have to give you a edge coloring of the complete graph without a monochromatic copy of a KT. So how I'm going to do it is I'm just going to color the edge set randomly in red or blue. So color each edge independently. Red, blue, probability half-half. And all you have to do is compute the expected number of monochromatic cliques. Monochromatic T. What you get is this is equal to n choose T. That's the number of ways to choose T vertices, and the probability that a single copy is monochromatic is 2 over 2 to the T choose 2, because there's 2 possibility of colors, red and blue. And so if you just plug in this number, you'll see that this is less than 1. Meaning there has to be a way to color so that there exists no monochromatic copies of KT, because this is always integer greater than or equal to 0. You can't always have a monochromatic copy, meaning there has to be one way of coloring where there are no monochromatic copies of KT. So this implies Ramsey number of k t is at most t minus 2 over 2. At least, thank you. Oh, probably saw this proof before. The reason I mentioned it is if you follow the exact same proof, what you can get is the following result. So exact same proof. If G has n vertices, m edges, then Ramsey number of G is at least 2 to the m over n minus 1. So let me just write this quantity as d of G. It's not a standard notation, but I'll just use it for today as the number of edges divided by the number of vertices. We can actually do a little bit better than this bound. So the Ramsey number of G is greater than or equal to 2 to the maximum over all subgraphs of G d of G prime minus 1. Okay. So this bound and this bound, it doesn't seem like a big difference, but you can easily cook up some examples where this bound is a lot better than this bound. So one example would be if you have a graph where this part is all sparse, and you have a tiny part which is, let's say, complete. Then you can adjust the parameter so that this part is overwhelming, and if you do the computation with this and this, you'll see that the second bound is a lot better than the first bound. So if you want to obtain a good general upper bound of the Ramsey number of graph, you have to capture this kind of behaviors, where some part of the graph can be a lot denser than the other part. So there is a class of graphs which exactly captures the concept that there are no denser subsets compared to the whole set. And it's called degenerate graphs. So a graph G is degenerate if all subsets of vertices, all subgraphs contain a vertex of degree at most d. First, note that this in particular implies if G is degenerate, then for all vertex subsets X, the number of edges inside X is at most D times X. The reason is if you take a subset X, just look at the vertex of lowest degree inside the subgraph induced on X. It has degree at most D. So you remove it. Then in the remaining graph, find another vertex which has the smallest degree. It has degree at most D. Continue, and then you can see that the total number of edges is at most D times X. Okay, for this class of graphs, if you fix D and just look at D degenerate graphs, this probabilistic bound becomes almost useless. Because the maximum over all subgraphs of G, the dg prime, is at most D always. What to say is for fixed D, that bound, all it gives, the bound above, gives the best it can give is 2 to the d minus 1. But this is a really stupid bound because there's a trivial bound, R of G being at least the number of vertices of the graph itself. Okay? So for this class of graphs, the probabilistic method bound doesn't give any useful information simply because your given graph is too sparse. That's probably the reason Burr and Erdős made the following conjecture. So they conjectured that for all natural numbers d, there exists a constant c depending on d, such that the Ramsey number of, let's set for all d degenerate graphs G, the Ramsey number of G is at most c times the number of vertices of G. Okay. And from now on, I'll just fix n to be the number of vertices of G. So, Cn. So what their conjecture says is that this trivial bound cannot be too far from the truth for this class of sparse graphs, sparse in a very uniform sense.
So d equals 1 is a forest?
D equals 1 is a forest, yes.
Then it's true.
Yes. Well, they actually, yeah, that's true. And in fact, the original conjecture was made in terms of a concept called arboricity, which is defined as the minimum number of forests you can into which you can decompose the edge set of the graph. So it's really closely related to forests and the sparsity. So this conjecture was made in 1973. And received quite a lot of attention since then. So let me show you some results. Okay, so the first result toward the conjecture was proved by Quatal, Rodel, Semiretti, and Trotter in 1983. So they weren't able to prove the conjecture, but they were able to prove it for a more restricted class of graphs, namely graphs with bounded max degree. So they proved that for all delta, there exists a constant c, such that for all graphs G, G of max degree at most delta, the Ramsey number of the graph is at most c times n. Namely, the conjecture is true if you look at bounded max degree graphs. And the real interesting story behind what I think is interesting story behind this theorem is that it was one of the first applications of Semiretti's regularity lemma, other than Semiretti's theorem itself. So by now, the technique is quite standard, but at that time, I would suspect it was a very interesting development. But on the other hand, that means, because it used Semiretti's regularity lemma, the constant c, the dependence between delta and c, is really bad. How bad is, like, it's actually a tower type dependency. So what they proved is c is at most 2 to the 2 to the 2 to the 2, where the number of 2's is some polynomial in delta. That's not a very good bound. And people were able to improve this bound since then by not using the regularity lemma. So the first improvement was made by Eaton in 1998. So she was able to prove that c is at most double exponential in delta. Then Graham, Rodel, and Ruchinsky they were able to improve it to almost single exponential, at most 2 to the c prime delta log square delta. And the current best bound is by Conlon, Fox, and Sudakov. They proved it in 2012. This one is 2000. at most. So they removed one of the log factors here. And that's the best known so far. On the other hand, it is known that you cannot do better than a single exponential. So Graham, Rodel, and Rachinski proved that the best you can go is down to a single exponential. And to understand what's going on here, you can think of it as the smallest, well, essentially max degree delta graph you have is a complete graph on delta plus 1 vertices. And for that one, the Ramsey number is known to be exponential in delta. So what this is saying is that that exponential part is fixed. And now if you increase the number of vertices, the Ramsey number scales as together with the number of vertices. So these Conlon, Fox, and Sudakov weren't able to actually prove that single exponential behavior, but got pretty close. Okay, so the next series of development, maybe it's not a series this time. So the next development on the conjecture was made in 1993 by Chen and Shelp. So what they proved is they proved the conjecture for a class of graphs with a class of sparse graphs where the measure of sparsity lies strictly between having bounded max degree and having bounded degeneracy. And I won't define it, but it's called, they define the concept of arrangeable graphs and prove that the conjecture is true for graphs of bounded arrangeability. So I won't define this, but in particular, it implies that it's true for planar graphs. And then,
What is default parameters?
excuse me?
I mean, is there some data parameters?
Oh, for planar graphs, if you consider Euler's formula, you can prove that planar graphs always have at most 6 times the number of vertices. So the number of edges is at most 6 times the number of vertices. 3 times the number of vertices, so the degree is at most 6. Yes. And so one graph, so I didn't define it, but one class which is not arrangeable but has bounded degeneracy is KT subdivisions. And Noga proved that this is true. Allen proved that it's true for KT subdivision. So people are slowly getting closer to degeneracy, one step at a time. And Noga's result, I believe, is from 1994. Okay, so now, then they wanted to know about the conjecture itself. We can't prove a linear bound, but how close can we get to a linear bound? Well, the first result in that direction was proved by Kostachka and Rodel. In 2004. They proved that the Ramsey number is at most quadratic. So C depends on D. And now we're talking about degenerate graphs G. So this result doesn't sacrifice on the measure of sparsity, but instead sacrifices on the bound. So we have a quadratic instead of a linear. So the breakthrough was made by Kostachka and Sudakov. After this, in 2003, they proved that the Ramsey number is almost linear in n. So n to the 1 plus little o of 1 of type. They showed this behavior where the explicit little o1 here is n times e to the square root of log n. Not square root, sorry. Log n to the 2d over 2d with some constant here. And the constant also depends on d. And Fox and Sudakov improved this in 2009 showed that this exponent doesn't have to depend on n. A lot of improvements. And so I would like to today report my progress. I was able to prove the conjecture of Bernoulli building on these results. So conjecture is true. And I really wanted to mention all these historical things because I build on all these work. And the main technique that I use here, well, before I go on to technique, let me show you the explicit bound I get is R of G is at most 2 to the C times D times N, where C is absolute constant. So it's linear and the constant depends double exponentially in D, at most double exponentially. So as mentioned already for bounded degree graphs, the best possible you can hope for on the other side is a single exponential. For degenerate graphs, it's even easier to see. If you consider the complete bipartite graph with d vertices in one part, n minus d vertices in the other part, then random number of this graph is at least 1 plus little times 2 to the d times n. And the reason is, first of all, this is degenerate. You can easily check it. And the reason this bound holds is simply take a complete graph on this many vertices and randomly color the edges in 2 colors. Then all D tuples have about n common neighbors because of how we randomly colored it. So in random coloring of Kn, each D tuple has about 2 to the minus dn common red neighbors, and similarly common red blue neighbors, because each one is like a random graph with probability half. And if you analyze it, you just get this bound. So we know that the constant is somewhere between single exponential and double exponential. And so that's what I want to talk about today. And the remaining part is to show you a proof of the toy case of this theorem. And so the main technique, what I was saying is the main technique I used is something called dependent random choice. It was starting to be developed around early 2000. So Kostachka and Rodo's result, they had a series of 2 papers. This one and another one that I will soon mention. And the other one, they first used this primitive form of this dependent random choice technique. And independently, another a lot earlier by a paper of Gowers, where he was interested in proving Semerity's theorem. He was interested in proving a theorem in additive combinatorics and had to reprove a theorem called Baloch-Gowers-Semerity theorem. And there, the same technique appears in a slightly different form. So that was kind of the early stage of the development. And the most relevant to me, was this result of Kostachka and Sudakov, where they really found a framework of applying it to degenerate graphs. So let me go into that in a little bit more detail. Okay, what do you want? So how I first got interested in the problem is because there was this toy case asked by Fox and Sudakov. They said, they asked in 2009, is the conjecture true for bipartite graphs with one part having bounded max degree. So the graph looks like this. We have two parts, A1 and A2. All vertices in one part have some bounded max degree. I'll just say D. But there's no restriction on the degree of the vertices in A2. So while studying, after they obtained this result, they were trying to push further and then realized that maybe this is a bottleneck. If you understand this case, it's likely you can go further and so on. So they pose this question, can we prove the conjecture for this case? And actually, already some partial results were known. If you look at it this way, there are results that can be interpreted as partial results towards this one. And the first one was by Noga in that paper about KT subdivisions. His result actually is a general theorem which implies this for D equals 2. And then Kostachka and Rodel, I think it's 2004. What they proved is this case is true if the number of vertices with unbounded degree is significantly smaller than the number of vertices with bounded degree. Namely, if there exists a gamma less than 1 such that A2 is less than A1 to the gamma. This is the wrong picture. A2 has to be smaller than A1. And if you really want to see why they thought it's important to understand this case, if you go into the proof of Kostachka and Rodel and see actually what that proof can give, what you can get is, it's true if A2 is at most A1 times e to the minus square root of log of A1. And the reason you have that e to the minus square root log, e to the square root log there is the same reason you have e to the square root log here. So their question is essentially, can we somehow get rid of that factor there? So I was able to answer their question and prove that. So what they asked, actually, we already know that Bernard's conjecture is true for that class of graphs because of this theorem. But in fact, we have a better bound for this particular case. Okay, so if G is as in the other board, as in left side, and n is sufficiently large, depending on D is a bounded degree on one part, then random number of G is at most 1 plus 2 to the minus D minus 2 to the n. But this is some small number. But basically, I can prove that the random number is at most 2 to the D times n for this particular case. And I was quite surprised because there is this lower bound on complete bipartite graphs, which actually this example also falls into this category, whose lower bound is about 2 to the n. So I can't prove it asymptotically because this term depends on D. But as D goes to infinity, I can show that the random number of this is the best possible upper bound on such class of graphs. Okay, so in the remaining time, I would like to show you the proof of this theorem with a slightly worse bound. So I think I'm actually showing 2 to the D plus 2 times n upper bound. And that proof already contains, I believe that it already contains all the main ideas behind this theorem, which is basically developing on this idea of Kostachka and Sudakov, and another application of dependent random choice developed by Alon, Krivlovich, and Sudakov. So let me mention when it gets relevant again. Okay, so there's two parts to this proof. Oh, so let me correct myself. So the proof of this theorem actually uses dependent random choice as in a paper of Noga and Michael Grigolovich and Benny Sudakov. And then to go from this theorem to the whole degenerate graphs, you can use the framework of here. So today what you're going to see is this technique developed by Alon, Grigolovich, and Sudakov. I think it was 2003, around that time. So the setting is as follows. You have a graph G, two parts A1 and A2. Just like this picture, I will assume that the vertices in A1 have bounded degree. Gamma is some graph, and the goal is to embed G to gamma. I won't specify yet what this graph is, just I will mention that it's a graph with density at least half. Okay? Even though this is a Ramsey result, I'm going to say just take one of the denser color among red and blue. Then in the denser color, the density is at least half. So for simplicity, I'm just assuming it's bipartite. And then let's say we have a graph of density at least half, large enough. Can we embed this graph into this graph so that A1 goes into V1, A2 goes into V2? So let me leave that picture there. So there are two lemmas. First lemma is the following. There exists a subset of V2 of size at least 1 over 8 times V2 such that I rushed too much. This quantity is less than half. I apologize, I should have defined this first. So there's one concept that I have to use to prove the theorem. And I named it the defect, but this concept already appeared in that paper. So let's say Q is a D2 pool of vertices in V2. Okay. This is, so Q is, I can write it down as V1, V2 up to VD. It's an ordered tuple of vertices, not necessarily distinct. And then I will define for this Q the defect, the theta defect actually. So theta is some parameter that I will define later, some real number. Can be anything, I will specify it later. This is 0 if the common neighbors of Q is at least theta, and otherwise I define it as theta over the common neighbors of Q. Okay. So why am I interested in this quantity? Here's my strategy of embedding G to gamma. So step 1, embed A2 to V2 randomly. And then step 2 is embed A1 to V1 greedily. Sounds like a very simple plan. To make this possible, I have to ensure that this embedding has some good properties. Let's see. If I embedded already A2 to V2, let's say there are only 5 vertices here. 1, 2, 3, 4, 5. And it went to or here, 1, 2, 3, 4, 5. Suppose that was the first embedding in the first step. And then assume that we had 2 vertices here, 1 and 2, each having 3 neighbors, like that. What we want to control is the number of common neighbors of these 3 vertices and the number of common neighbors of these 3 vertices. So in this particular case, I want to make sure that these 3 vertices have at least 1 common neighbor. And if I want to use a greedy algorithm, I want to make sure that these 3 vertices have at least 2 common neighbors. Because if that's the case, they have at least 1 common neighbor. I will embed 1 to that common neighbor. These 3 have at least 2 common neighbors. Even if I happen to already use one of it, I can use the other one to embed 2 to the other one. So in that sense, I have to understand the number of common neighbors of the D tuples in V2. And this definition of defect is one way to capture it analytically. So what I have is this threshold theta. If the number of common neighbors of my D tuple is greater than this threshold, I don't care, because I just need a certain amount. So in that case, I say it has no defect, it's a perfect D tuple. Otherwise, if they don't have enough common neighbors, as much as I want them to, then according to how much less they have, I give defect proportional to the inverse of the number of common neighbors. So in particular, if I have a D tuple with 0 common neighbors, then it has infinite defect, meaning I probably don't want to use it. OK. So now let me go back to the lemma. Theta, I have to
be the size of V1?
Exactly, yes, A1.
Okay,
So I will use theta to be the size of A1. Because under that greedy algorithm, if I have at least A1 common neighbors, then at that point, I don't have to worry about how much more it has. But if it has less, I do want to know how much less it has. So what this lemma says is I can find a subset of V2. So this is a preparation for my first embedding. It's not yet the embedding. It says I can find a subset of V2, quite large, where the average defect over all D tuples is small. This quantity is just so sum up all the defects over all possible D tuples in your set X, and divide by the number of D tuples. In other words, this is the average defect in my set X over all D tuples. And it happens to be less than 1/2, meaning for most of them, the defect is pretty much 0. So most of the D tuples in my set will have many common neighbors. So that kind of...
Well, why do you say it's most of them?
Because if it's less than half, if the average is less than half, well, most of them is not the exact right word here. Just you would expect a lot of them to have the right number. Well, the reason I say most of it is actually it's 0 or it's at least 1. So at least half has 0. Yeah. OK. So this lemma here can be proved using dependent random choice. I believe I don't have time, but if I have time, I'll come back to it. Let me show how to prove the theorem using that lemma. Let's go back to this thing. The first step, as I said, I want to embed A2 to V2 randomly. So let me first state the exact theorem I want to prove. OK, so lemma. If V1 is at least 2 to the D plus 1 times A1, and V2 is at least, I think 16 will work here, then G is contained in gamma. OK. So I will use theta to be equal to A1, as Noga said. Now let's embed it according to these steps. In step 1, I will take a random map from A2 to V2, but I want it to be injection. So take a random injection phi from A2 to V2. Random uniform injection. No, this is not right. A2 to X, where X is a set from lemma 1. Inside V2, I can find a set X satisfying these two properties. Because V2 is at least 16 times A2, X is at least 2 times A2. So I have enough space to find an injection from A2 to X. Out of all possible injections, just take a random uniform injection. And the key quantity I want to understand is the expected value over all vertices in A1, the defect of the D tuple consisting of where the neighbors of X went to. So assume all vertices have exactly D neighbors. In A1. All vertices in A1. So what I'm computing here is, for each vertex here, look at where these D tuples went to. And I'm trying to understand how much is the defect of this plus how much is the defect of that. At a more larger scale, of course. Because those are the D tuples that I'm interested in. That is already embedded. Because A2 is embedded to V2, these ones already have some fixed image according to phi. That phi is good enough only when the images have some good property. And I'm trying to say that it has a good property if I can control this total sum of the defect over all possible vertices. And this computation is quite easy, actually, because by linearity of expectation, I can put the sum out. This is expected value of a single defect. Okay. And this one is sum over all A1, sum over all D tuples in X. The defect of Q times the probability that the neighbors got mapped exactly to Q. I just sorted it out. Now, here is a slight abuse of notation because I said Q is an ordered D tuple, neighbored is just a set. So assume neighbored is just some ordered D tuple of vertices consisting of same set. And you can compute this probability exactly. So it's sum over all A1, sum over Q and X to the D, weight of Q, times 1 over, the first vertex has to go to the first vertex of Q. That's 1 over X. Second has to go to the second, X minus 1, dot X minus D plus 1. Because I'm looking at a random injection. Actually, I cheated a little bit here, because if two vertices of Q are the same, the probability is 0. It's not this. I'm slightly cheating here. There is some small correction term here, but
why do you use D tuples and not sets of size D? Use a defect.
It just made my computation easier because I have to write X choose D here and everything. There's there is a choice, but each choice has different sorts of complications coming, and you have to sort it out at one point. Okay, so it's easy to see that it doesn't depend on x, so I'll just write a1 times this. And this quantity, if I just cheat a little bit and say this is x to the d, this quantity is exactly what I'm controlling here, the average defect over all d tuples in x. And the reason I bounded above by half is because this is not exactly x to the d. So let me just say this is at most a1. Okay, I lose a little bit here, but I can make it up because I have 1/2 there. Okay, so we're almost there. So how does the greedy embedding work? Greedy embedding works as follows. So order the vertices in A1 as x1, x2, x3, ... so that the quantity we're interested in, the defect of where its neighborhood went to, neighborhood of x1, is decreasing. So my plan is to embed greedily vertices one at a time, and I want to embed vertices with large defect first. It makes sense because large defect means small number of common neighbors. If you have small number of common neighbors, it's probably a better idea to embed those ones first. Just like in the case, if these three had one common neighbor, these three had two common neighbors, it's better to do this first and then this. If you do it the other way, you might get stuck. So I will embed according to this ordering. Embed greedily following this order. Okay, when we try to embed ith vertex, let's see what happens. There's two cases. Case 1, this defect is 0. That means the definition just implies that the common neighbors, I'll just write common neighbors because the notation will get pretty bad, of where the neighbors of xi went to, this is at least theta, which I define to be a1. So if case 1 happens, no matter what happened before, I already have enough common neighbors of where the neighbors of I went to. Meaning, pick as image of xi arbitrary vertex not used in the common neighbor. Now, the main case is, of course, the second case when it's not equal to 0. What we know then is that omega, the defect of what we're interested in, is at most 1 over I times the defect of the first vertex plus the defect of the second vertex, and so on to the ith vertex. Let's give a crude upper bound on this of the total sum. This is at most a1 over I, which is theta over I. On the other hand, the definition of defect, well, it's theta over the number of common neighbors. Notation is pretty bad. So I'll again write common neighbors of phi of nxi. Theta was chosen to be equal to a1, so let me write this as theta. So if you reverse it, what you get is the number of common neighbors of where your neighbors of xi went to is at least I. And that has essentially the exact same effect as having at least theta common neighbors. because when you're embedding the ith vertex, you so far only embedded at most I-1 vertices. Meaning, having common neighbors at least I is essentially the same. You can just apply the same argument. So it works.
It also gives motivation for the definition, right?
Yes. The inverse. It's not very clear why we have to use the inverse here. There's a lot of choices. Somehow inverse works nicely here. Oh. As I said, another ingredient that I use to get to the whole proof is a framework developed by Kostachka and Surakov to get the whole thing. And if you want to prove the lemma, it's called dependent random choice. If you want to go back and check, how you find your set X is in lemma 1. To find X, do the following. Take two vertices V1 and V2 in large set V1 independently and uniformly at random. Then define X as a common neighbor of V1 and V2. So what I want to do is take V1 randomly, take V2 randomly. That will be my X. And that's where the name dependent random choice comes from. You have a random choice, but the actual set that you're interested in, X, is dependent on these random choices. So that means it's a bit harder to control the exact set X, but somehow magically you can do it. That's the beauty of dependent random choice. So if you've never seen it before, it's a really beautiful topic. So there's a survey by Fox and Surakov, and also a chapter in Noga's book. Not a chapter, but that probabilistic lens, so a few pages. And so, yeah, it's a beautiful thing. And so that's it. That's all I wanted to say. Thank you.
Thank you.